So good morning, I'm Tagami. I'm from KDDI Research. And so I'm show about my paper entitled Stardust and Panoramic Drive Electronic on ICN. This is collaborative work with KDDI Research and Kozo Keikaku Engineering and the University of Goettingen and the University of London and so Osaka University. Okay, so panoramic video is became popular because some head-mount display or on video camera becomes cheaper, and so we can get them, and so we can create panoramic video easily. So the traffic broadcasted to grow 11-fold from 2016 to 2021. But so panoramic video requires a high spectral, high resolution. For example, 4K, 8K, 60K, and then there are how to deliver this video streaming is very important issue for the future internet. And so we propose a panoramic video streaming system on ICN. We already demonstrated on ACN, ICN, or CEBIT, or ICN meeting. So today we explain about our design of this streaming system and so its evaluation. So first is panoramic video streaming. So panoramic video is captured by the omnidirectional camera, and that this camera can capture 360 degree view. And so a user can fully control his viewing direction, and so user selects a part of the video frame, and so shows this user view. And so if user moves to the around, so that area is also changes, and so user can show the like some 360 views. So of course, user only was on this part of video frame, and then first the tile-based panoramic video streaming is proposed, which is separate the video frame by type. And so user request necessary tiles depend on the user's field of view. In this case, the network can reduce the traffic because some user request only the necessary tiles. And so we our idea is a named tile-based video streaming. We assign a unique name for each tile, and so each user requests each tile by name. In this case, on ICN, so the intermediate router can aggregate some same request, and then if these two users request the same tile, intermediate router aggregate this request, and so receiver received only one request, and back to the only one tile and separate like a multicast query. In this case, we can reduce the traffic between the producer and intermediate router. But so in this case, we cannot decrease the traffic on the last one hop. This is the access network traffic. And then next idea is multi-level quality tiles. So this idea is we produce prepare the multi-level quality tile. For example, low quality tile and high quality tile. And so the user select different tiles. So for example, the user requests a low quality tile where user does not focus on the attention. For example, the outside of the side or edge of the side. Usually use the focus the center of the side, and then even if the edge of side chord is lower, but let's say user not pay attention. And then we can reduce bandwidth with degrading QoE. So on the ICN, so on ICN, and then we can decrease the access network traffic. But so that lead on some demerit. So this means multi-level tiling means some increase the variation of types. For example, for two users request the same type, but one user requests high quality type, but another user requests low quality type. In this case, the router cannot aggregate this request because the user requests other types. And then we cannot decrease the core network traffic. So to avoid this demerit, we introduce a transcoder on the intermediate router. For example, one user requests high quality type and another user requests low quality type. Intermediate router exchange the transcoder and high quality type to the low quality type. In this case, the router requests only the high quality type, and so receive high quality type, and so router transcode the high quality type to the low quality type and back to the users. In this case, we can reduce the access network traffic and core network traffic. So to achieve this system, so we use a keyword-based naming scheme. Keyword-based name scheme consists of the domain location, which means there are some service identification, and so network function. In this case, we use a function transport. And so information. Information is consistent of sequence number of video frame and tiles position. Using this name scheme, for user, when user requests a lower quality type, the user adds the prefix function transcoding. And so transcoder advertises this prefix root, and then this requests forward to the transcoder, and transcoder requests a high quality type, and so we can achieve this system. So next evaluation. On this paper, we show many evaluations. So today I show two evaluations. One is the traffic reduction, and so one is the processing time. This is a evaluate configuration. We use 4K video, 6 video, and so we use with a tile. One tile is 500 millisecond MP4 video. And so we separate the video frame to the 100 tiles, and so we use a suit consumer which change the field of the run. And so first, this graph shows traffic reduction on the access network. Using multi-level quality tiles, we can reduce about 20% traffic on the access network. So next graph shows the traffic over the core network. Blue line means without cache, and so green lines are with cache. With the caching and so request aggregation on the intermediate route, we can reduce the traffic. And so red line is cache with cache and transcoding. When the number of consumers is small, so this transcoder requests always high quality tiles. Then core network traffic keeps increasing, but so then the number of consumers larger, the traffic is less than the with transport. And so next evaluation is processing time. So our system scheme is the first video capture video frame, and so the producer encodes the frame to the video file, and so divide to the file to the segment with the size of ICN packet, data packet, and so encrypt this segment by SCS, and so signature assigned to each packet using RSA or something. We measure this for process time. So this is a result version. So actually, we use H.264 and MP4. So H.264 provides a smaller size video frame size, but it required more encoding time. So MP4 requires small encoding time, but so it compensated not small. Then so there are many segments. Within segments, then some producer should sign many packets, and then simulated times became longer than the H.2.6. So actually, we use a 500 millisecond video time, and then we separate 100 tiles for each frame, and then we should process only 5 milliseconds for each tile. And then actually this MP4 and HMAC is acceptable rate using a multi-core. When we use a 4-core, we can make this tile for 5 milliseconds. But so actually HMAC is HMAC use the same key both of the two sign and to verify the packet. And then it is not this HMAC is means so needs the same key, and then it is not good. And then we propose a new manifesto signature scheme. This is this scheme is encryption after encryption. So calculate the hash value instead of the first packet, and to add this hash value to the first packet, and so only the sign on the first packet. In this case, consumer can verify the first packet using this sign, and so other packet by this hash. So in this case, we can reduce the segment time. But so of course, it is not enough for the. We need 8 core to the this making this time. But so we can do this. Sorry. So conclusion. So we developed the plan. So actually, we published this demo system, include the producer and consumer. Consumer is written by the JavaScript, and so on the GitHub. And so please show this report. Thank you.
The next question. Yeah.
First of all, thanks for your attention. Thanks for your presentation. I have a question about the evaluation part. And the time duration of till is 100. Means that So this is a traditional setting, or you made this by your own. You made this on
500 millisecond means some first we capture some video 5 millisecond, and so we make a video frame for the 500 millisecond, and so this means there's some this turns we correct the video frame for 500 millisecond, and so create a small video file for 500 milliseconds.
Okay. And what about the frame rate?
Frame rate is kind of 30 frames per second. This means 30.
Yeah.
This means and then this means 50 frames to the 1 file.
Okay. And for the simulation figure, there is a cross point. Yeah, this is a white line and green line, and there's a cross point. And
Yeah.
before the point, it seems that the red line performance is bad. It seems that the green line performance is better. So
Yes. When number of consumers is smaller, in this case, our transcoding mechanism. So even if only there's only the users to request lower time, in this case, transcoder request always higher frame. It is not good. I understand, but so currently we does not have solution for this. But and then when the number of consumers small, this traffic becomes better.
okay, thank you.
Did you play with the different tile sizes besides this 10 by 10?
Yes. So on this paper we showed this evaluation. So the larger time the traffic becomes more larger because we need to use some more pixels so over the field of view. And so smaller tiles is too small, and so compressed rate becomes large, and then we cannot. It is good, not good. And then actually 100 is the best for the traffic for one consumer.
I have a question
Yeah.
for the in-network adaptation part. So you basically have to re-encode the videos in the network, and you re-sign the video in the network, basically. So which means the router signs on each packet. But shouldn't the producer do this, create the signature of the packet? Because if any router in the network
Yes,
signs the packet, it could be a security issue.
Yeah, full write signature is I think serious problem. So in this case, currently we assume the hierarchical key scheme using hierarchical scheme, and so users can verify some who create this packet. And so other idea is using producer signed and on sign and transporter signed on sign. And so other times somewhere we manage or we show the relationship of each sign. For example, this transcoder can transcode this producer's data. It is some hierarchical and so user can use this hierarchy and so sign and so verify the packet.